Hello, and welcome to EEforEveryone. Today we're going to talk about ground. No, not the sand, dirt, gravel, or ice that your house is built on, but electrical ground. Ground is a very interesting concept with more complexities than you may be aware of. Let's start with an example. Let's say that we want to build a circuit, but not just any circuit, a voltage source that supplies 10 volts which is applied across a 100 ohm resistor. Now when I begin to think about how I might accomplish that, there are two intuitive schematics that come to mind. I'll display the two circuit schematics on the screen, and I think that my design intent will be intuitively obvious. You can see the two circuits, clearly labeled Circuit 1 and Circuit 2, but what is the difference between these two circuits? Both circuits would behave identically as far as I'm concerned. They would both apply 10 volts to the resistor and both have 100 milliamps flowing through the resistors. But surely there must be a difference here because one circuit has 3 components and the other has 2. The difference would be made clear if the terminal of V1 was connected to the positive terminal of V2, or if someone decided to touch the resistor R1. Obviously, the difference is that the negative side of circuit 1 is at a potential of 10 kilovolts, while the negative side of circuit 2 is at a potential of 0 kilovolts. But what reference point are we measuring from? If you take your multimeter and put one lead on the negative side of V1, where should you put the other lead of your multimeter to measure the 10 kilovolt potential? The answer to that, as the people in the front of the class have probably guessed, is ground. That is, stick a big metal rod into the earth and put the other lead of your multimeter onto that metal rod. That is how you will measure the 10 kilovolt potential across V3. Okay, so why do we want to use the earth as the reference voltage for our circuits? To be honest, I don't know the real answer because I don't know the person who made the decision. Perhaps it's because they charged the Earth to a potential of 10 kilovolts with respect to the moon, and that just felt like the right reference point. Jokes aside, I think that I can think of a few good reasons why we use Earth ground potential as a reference point for nearly all of our voltage measurements. 1. Everything is coupled to Earth ground, even if it's not directly connected. No matter how hard we try, there will always be at least some capacitive coupling from every circuit to ground. Granted, the coupling is a lot weaker for an airplane during flight than for a sheet of metal 10 centimeters above the dirt, but everything is capacitively coupled to ground. Plus, if you're walking on or sitting on the ground, then your body will be eventually at the same voltage potential as the ground, which leads us to point 2, shock hazards. If we don't use the ground as the reference point for our circuits and you're standing on the ground, so you're at ground potential and the circuit you want to interact with may or may not be any number of volts above or below your potential. What this boils down to is that even if a circuit was designed to operate at 10 volts, but that's not 10 volts with respect to ground, technically it could be 10 volts with respect to 10 kilovolts from your current potential, without there being a fault in the design. Ensuring that 10 volts is actually 10 volts with respect to ground allows us to know instantly that a 10 volt circuit is not a shock hazard. 3. Intercompatibility. Let's say you wanted to lay a copper cable between 2 data centers 10 kilometers away. Before you think about it, you connect the 2 data centers' reference voltages together when you're greeted with a blown circuit breaker and melted wires. What you forgot is that these data centers use different reference voltage potentials, and you just shorted them out. That's a bad situation, because if both reference potentials are truly isolated from ground, then you could have applied any number of volts across that cable, that interface that you meant to connect. We'll come back to this point in a moment. To avoid situations like this, we all universally agreed that the reference voltage should be ground. That last story brings up a good point though. The Earth isn't made completely of conductive material, so how can ground be the same potential everywhere? The short answer is that it's not, and that's something that engineers work hard to mitigate. By mitigate, I mean counteract the potential negative effects that ground being a different voltage in two places could present. To summarize, electrical ground is the reference point where all other voltages are measured from, and we've all decided, for the overall greater good, that the reference point should be the portion of the Earth that we are standing on top of. I have a quick example about ground that will hopefully help you to see why having two different ground potentials can pose an issue for electronics, and what might happen if we directly connected two systems with different ground potentials together. This LT-SPICE simulation shows a couple of principles at once. On the bottom, there are many voltage sources labeled VG. These are simulating the voltage gradient from one point to another underneath the surface of the Earth. The point that I'm trying to demonstrate here is that there isn't a voltage source under the ground, where once you cross a certain point the voltage changes, but it's more of a gradual change from one potential to another. You can also see resistance where you may have expected to see a wire, and that is R2 through R21. These resistors are simulating the resistance of the copper wire that is connecting these 2 points. The resistance of a piece of wire can be calculated using the resistivity of the material, the cross-sectional area, and the length of the wire. In this case, we are assuming that over whatever distance could create a 10-volt difference in the ground potential between 2 points could require a length of wire to connect them that would result in 100 ohms of resistance. Then we have a microcontroller outputting a pulse train with 50% duty cycle, swaying from 0 volts above its ground potential to 5 volts above its local ground potential. This ground potential, local to our outputting microcontroller, is labeled remote ground. This signal is fed through our not ideal wire and eventually comes back to the 5-volt tolerant input of our receiving microcontroller. Where we are, at this point near our receiving microcontroller, is expecting no more than 5 volts with respect to its local ground potential. This local ground potential is labeled with the ground symbol in LT-SPICE. Running the simulation, if we plot the pulse train at the output of the remote microcontroller with respect to its local ground, we can see the signal varying from 0 volts to 5 volts, as we would expect. Now if we plot that same signal where it connects to the microcontroller that's receiving the signal, it looks similar, but it's varying from 10 to 15 volts instead of from 0 to 5. What's going on here? Even more perplexing is that the bottom chain of resistors that's representing our ground conductor, or the conductor connecting ground to ground, is carrying 100 milliamps through it, but it's connecting ground to ground, so we would typically expect that it would carry no current, except for the return from the output of our microcontroller. Of course, the reason for this current and voltage shift is made obvious when we can see the voltage potential underneath the ground, or underneath the Earth's surface. But it isn't always practical to measure the difference in ground potential between 2 points that are miles apart. That's ultimately what causes issues in systems that are separated by distance when they don't have proper considerations for the potential difference in ground between 2 points, and demonstrates the point of why we all universally decided to use ground as our reference voltage. Say these two systems were intentionally designed to use 2 different return potentials, or it's difficult to not say ground because I'm so used to it, but whatever their voltage reference point was, if one intentionally used 100 volts instead of 0 with respect to earth ground, this issue would be systematic when trying to connect different systems from different vendors. To avoid that, we all just decided that the ground underneath our feet should be ground. So, that's ground. If you would like me to follow up on these concepts by discussing how to prevent damage to the 5-volt tolerant microcontroller in our last example, or expand on this topic by adding in the parasitic capacitance and inductance into our model of a wire, let me know in the comments. I hope that you found this video interesting and enjoyed my jokes as much as I enjoy LT Spice. If you're enjoying these videos, please subscribe to this channel as a token of your appreciation. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!